oil in the cables. So the low viscosity oil is kept under pressure and fills the voids in the oil impregnated paper under all conditions of the varying load. So there are three main types of the oil filled cables: self-contained circular type, self-contained flat type, and the pipe type cables. So we have three types of the oil filled cables. So this is the oil filled cables assembly are there. So this is the outer part or the sheath which is grooved at various intervals, and oil is allowed to flow in this oil channels. This is the paper insulation, this is the conductor, and in the sheath, in the outer sheath, we have the oil channels in which the oil is flowing and working as a insulator as well as a dielectric material. And in the second type we can also see which is having the various oil ducts are there. These are the conductors, paper insulation is there, and in these parts we are having the oil ducts. We can see the three ducts are there. These are the oil ducts in which the oil is flowing at some pressure. Then we have some advantages of this oil filled cables. First is the greater operating dielectric stresses. Then the greater working temperature and current carrying capacity. Better impregnation, and impregnation is possible after sheath no void formation, and the smaller size of cable due to reduced dielectric thickness, and the defect can easily be detected by the oil leakage. Then we have the gas pressure cables. In these cables, an inert gas like nitrogen is used to exert pressure on the paper dielectric to prevent the void formation, and these are also termed as compression cables. And the insulated cores similar to the solid type, and the cable is inserted in a pressure vessel which may be a rigid steel pipe, which is commonly known as pipeline compression cable. The nitrogen gas is filled in a vessel at nominal pressure of 1.38 into 10 raised to power exponential 6 Newton square meter with a maximum pressure of 1.725 into 10 raised to power exponential of 6 Newton square meter. So this is the diagram of the gas pressure cables. Then we have the gas insulated cables, GIC. So in GIC cables, high pressure SF6, that is sulfur hexafluoride, is filled with small spaces in oil impregnated paper insulation and suppresses the ionization. The most EHV and UHV lines insulated with SF6 gas are being used extensively for the voltages above 132 kV to 1200 kV. And these cables are very popular for short lengths, river crossings and highway crossings. So this is the gas insulated cables GIC. You can see the diagram. This is the outer pipe in which SF6 gas is filled at 3 to 5 or to 6 bars of pressure. Then it has the spacers are there. You can see in this diagram. This is the outer pipe which is shown over here. Then this is the conductor. We can see in the inner part. This is the conductor. This is the insulation, and these are the spacers on which the central part is mounted in the outer pipe. So this is the flexible SF6 insulated cable which is used for 220 kV. Then we have the advantages of GIC, gas insulated cables. Advantages are there. So the gas insulated cables have the several advantages over the oil filled cables. First is the efficient heat transfer properties. So you can say that it can carry more current because the heat transfer efficiency is higher in the GIC. Second advantage is low dielectric loss and low capacitance. Low dielectric loss and low capacitance. Then SF6 is non-toxic, chemically stable and non-inflammable. And the terminations of GIC cable are simple and cheaper. Next we have the laying of the underground cables, which is very important part. So the reliability of the underground cable network, it depends upon the considerable extent upon the proper laying. Then we have the three main methods of laying the underground cables. First is the direct laying, then the draw-in system, and the solid system. So the three ways of cable laying are there: direct, draw-in, and solid system. First is the direct laying method. So this is a very cheap, simple, and the most likely to be used in the practice method. This is the most simple. Just dig a trench, lay the cable, and covered with concrete or with the soil. So a trench of about 1.5 meters deep and about 45 centimeter wide is dug. So the trench, the depth and the width of the trenches depends upon the type of cable and the number of cables. Then the cable is being laid inside the trench, and it can be covered with concrete or bricks in order to protect it from the mechanical injuries. Then it is covered with the soil, and it gives the better heat dissipating conditions under the earth. And this is the clean and very safe method, direct laying, and this is also very cheap method. It's the most economical method of direct laying. We can see this is the trench is there. Just dig a trench and put the cables, then again put the soil, again put the soil over the cable, then our purpose is solved. That is called the direct laying. Then we have some disadvantages of this direct laying. First is the localization of the fault is very difficult. In case there is any fault in the cable, we have to dig the complete system, then we have to locate the fault, and it is very difficult, which is the localization of the fault is very difficult, and it can be costlier in the congested areas where the excavation is expensive and inconvenient. And third, the maintenance cost of the direct laying is very high. Then we have the draw-in system. In this system, the conduit or duct of concrete is laid in the ground with the main holes at suitable positions along the cable routes, and then the cables are pulled into the positions from the main holes, as we will see in the next diagram. So the concrete is there, and we have put the cables on the channels which are inserted in this concrete. So this is called the draw-in system. Then we have some advantages and disadvantages of the draw-in system. First, it is having very high initial cost because of the laying of concrete in the trench, and the angles of iron are there. So the maintenance or the initial cost of this type of laying is very costly, and the heat dissipation conditions are not so good as compared to the direct laying, because the concrete is there, it has its own properties of heat transferability which are not as good as the soil is, and the advantage is that this method is very suitable for the congested areas where the excavation is expensive and inconvenient. So it is generally used for the short length cables, such as in the workshops, in the road crossings, where frequent digging is costlier and impossible. So the draw-in system, you can use them in such areas where the frequent digging is not possible. Then we have the solid system. So in this system, the cable is laid in the open pipes or throws dug out in the earth along with the cable route. The troughing is of cast iron or the treated wood, and this troughing is filled with the bituminous or concrete after the cables is laid. It provides very good mechanical strength, but the heat dissipation properties, the heat dissipation conditions are very poor. And it requires very skilled labor and the favorable weather conditions, and it is the most expensive system. It's a very expensive system. So as we can see, this is the solid system in which the cables are laid into the trenches, which are having some pipes are there, and the cables are put in these pipes, and then these pipes are filled with the concrete or some bituminous material. We will see in the next diagram the original solid system. This is the original solid system is there. We are having the various pipes are there in which the cables are inserted. Then these pipes are filled with the concrete or some other material. And this is the actual diagram of the solid system. Then we have the grading of the cables. So since the stresses are maximum at the surface of the conductor or innermost part of the dielectric, the stress goes on decreasing as the outermost layer is reached. Since the process of achieving the uniform electrostatic stresses on the dielectric of the cables is known as the grading of the cables. The unequal distribution of stresses is undesirable because if the dielectric is chosen according to maximum stress, the thickness of the cable increases, or either this may lead to the breakdown of the insulation. So we are having two main methods of the grading of the cables. First is the capacitance grading, and second is the intersheath grading. So two types of grading is there: capacitance grading and intersheath grading. So first is the capacitance grading. So in this method of grading, the insulation material which is used for the insulation of the cable, it should consist of various layers having different permittivities. So consider a cable graded by means of 3 layers of insulation having permittivities 1, 2 and 3 respectively. So let the outer radii of these layers by R1, R2 and R3 is equal to R respectively, and conductor radius is r. In order to secure the same value of the maximum stress in each layer, the maximum stresses in the layers are equated. Let the voltage across the innermost layer of insulation be V1. So when we compare all these three permittivities, V1 is zeta maximum R log E, R1 divided by R. So this is the capacitance grading method from where we can achieve voltage gradient of the first layer. Similarly, V2 and V3 can be determined. So by grading the insulation without increasing the overall diameter of the cable, the operating voltage can be raised. The difficulty with this method is that we can't obtain a wide range of permittivities in practice, as the paper insulation has permittivities that are limited to the range of 2.8 to 4. So in the above analysis, it has been assumed that the maximum permissible stress is the same for all the three dielectric used. If the maximum stress in the three sections are different and are 1, 2, 3 respectively, then the maximum stresses should be reached at the same time for the most economical operation of the insulation. Then we have the intersheath grading. In this method of grading, the same insulating material is used throughout the cable, but it is divided into 2 or more layers by means of the cylindrical screens or intersheaths. These intersheaths are connected to the tappings from the supply transformer. And the potentials are maintained at such values that each layer of insulation takes its proper share of the total voltage. The intersheaths are relatively flimsy and meant to carry only the charging current. Since there is a definite potential difference between the inner and outer radii of each sheath, so we can treat each section separately as a single core cable. If V1, V2, V3 are the potential differences across the sections of the insulation, then the cable insulation consists of a number of capacitors in series, which are formed by the respective intersheaths having all potential differences V1, V2 and V3 are in phase. Hence, if V is the phase to neutral voltage, then we can also write that V is equal to V1 plus V2 plus V3 up to Vn. Now we have the types of cable faults. The cables are generally laid in the ground or in the ducts in the underground distribution system. For this reason, there are little chances of faults in the underground cables, but if a fault does occur, it is difficult to locate and repair because the conductors are not visible. So the most likely faults that occur on the underground cables are open circuit fault, short circuit fault, and the earth fault. So in the open circuit faults, when there is a break in the conductor of a cable, it is called the open circuit fault. To locate the position of the open circuit fault, we can use the Megger. For this purpose, the three conductors of the three core cables at far end are shorted and earthed. The resistance between each conductor and earth is measured by the Megger, and it will indicate zero resistance in the circuit of conductor which is not broken. However, if the conductor is broken, the Megger will indicate infinite resistance in its circuit. Then the short circuit faults, when two conductors of a multi-core cable come in electrical contact with each other. This is called the short circuit. Again, we can seek the help of Megger to check this fault. For this purpose, the two terminals of the Megger are connected to any two conductors. If the Megger gives zero reading, it indicates a short circuit fault between these two conductors, and same steps can be repeated for other conductors. Then we have the earth faults. When the conductor of a cable comes in contact with earth, it is called earth fault or the ground fault. To identify this fault, one terminal of the Megger is connected to the conductor and the other terminal connected to earth. If the Megger indicates zero reading, it means the conductor is earthed, and the same procedure can be repeated for the other conductors of the cable. And the physical limitations of the underground cables. The first, they are the costs, then the laws of physics, how physically long power line can be. The higher voltage, the shorter the line length, and the limiting effects are very important. Then we have the physical limitations, the effect of capacitance is there. Then we have the summary of costs, overhead versus underground transmission. Underground may be 4 to 20 times of the overhead costs. Then the sub-transmission, underground may be 4 to 20 times of overhead. Distribution, the underground may be 2 to 10 times of the overhead. And the new undergrounds may be cheaper than overhead in special conditions, and cost varies greatly from the utility to utility and place to place. Thank you.